Okay, so we've learned about using balancing chemical equations, using the concept of the mole to do some basic calculations and conversions. But here's where we come to the real power of the chemical equation and the usefulness of balanced chemical equations. And that's in using the balanced chemical equation and the mole concept together to keep track of mass during a reaction. So if we just look at basic chemical equation here, we've got two molecules of hydrogen gas, H2, reacting with one molecule of oxygen gas, giving me two water molecules. If we look at that from a molecular perspective, we can see it just in a cartoon depiction here. If we just show balls as being the individual atoms, we can see our two H2 molecules, our one O2 molecule, and our two H2O molecules. And we can see that this is the ratios that the individual, that the molecules react with each other in order to generate the products. If we look at that, if we take those individual numbers or those individual coefficients, the number of molecules, if we were to scale this by any factor, and let's just say that we scaled it by a large factor, 6.022 times 10 to the 23rd, it would still function the same. We would still have the same ratio of molecules reacting with each other. And since 6.022 times 10 to the 23rd is the conversion between molecules and moles, we can say that the molecular interpretation is the same as the mole level interpretation. There's 2 moles of hydrogen gas will react with 1 mole of oxygen gas to generate 2 moles of water gas, or not water gas, in this case water liquid, water molecules. And if we take those moles and knowing the molar mass from the periodic table, we can say that 2 moles of H2 gas is equal to 4.0 grams of H2 gas. And if we convert moles of O2 to grams using its molar mass, and its molar mass is 32 grams per mole, then if we have 1 mole, then we would have 32.0 grams of O2. And if we do the same thing, we come out with 2 moles of water, we use its molar mass, and we come out and we convert that to grams, we come out with 36 grams. What we will notice is that this now matches the conservation of mass. We have 4 grams of hydrogen reacting with 32 grams of oxygen, and that generates 36 grams of water, which is all balanced. And so we have to just pay attention to a couple things here. We can note that the chemical equation only relates things in terms of number of molecules or number of moles. The coefficients do not relate them the molecules in terms of their masses directly. We can use the molar mass and convert to mass, but we can notice that the ratio here is not a mass ratio, it's always a mole ratio. But we have now a very useful factor from the chemical equation now, which is that the balanced chemical equation gives us molar equivalencies. What does that mean? It means that there are 2 moles of hydrogen reacting with 1 mole of oxygen. I can treat that as an equivalency. 2 moles of hydrogen is equal to 1 mole of oxygen in the chemical equation. 2 moles of hydrogen is equal to 2 moles of water. In the chemical equation, those things are related to each other. And those now become conversion factors. Let's show this as an example. When 1.57 moles of oxygen reacts with hydrogen to form water, how many moles of hydrogen are consumed? Well, I look at the balanced chemical equation, and I can say that there's 2 moles of hydrogen gas for every 1 mole of oxygen gas. So the relationship here, the molar equivalency, is that 2 moles of hydrogen is equal to 1 mole of oxygen. And thus that becomes now an equality and a conversion factor that I can use. 1 mole of O2 is equal to 2 moles of H2. And so I start with my moles of O2, and then I put moles of O2 from my conversion factor on the bottom, moles of H2 on top. The moles of O2 cancel, leaving me with moles of H2, and I multiply through, and I come out with a certain number of moles of H2 for this. Let's take it a step further. So let's say that in the reaction above, that one of the cases when somebody ran this, they generated 2.14 grams of water. What mass of oxygen was consumed? And what we're given the molar masses for water being 18.02 grams per mole, and we're given the molar mass for O2 as 16.00 grams per mole. So I have 2.14 grams of water, and I want to figure out how much mass of oxygen was there that I started with. Well, I can use the conversion factors such as molar mass and the molar equivalencies to relate these two things. I don't have anything initially that relates the mass of water to the mass of oxygen, but I do have a chemical equation that relates the molar amounts. So I have a process here. Whenever I have grams of one substance, and I want to figure out how many grams of a different substance are related to that. Either in this case, it would be used to generate that, or maybe if I started with a mass on the reactant side, how much mass of product would I get from there? I will start with the grams of substance A, whatever it is, and use the molar mass first to convert the grams of A to moles of A, because the chemical equation relates molecules in terms of their number of moles, not their mass, but their number of moles. And so then I can convert between moles of substance A and moles of substance B, just as I did above here when I was converting between moles of O2 and moles of H2. And then once I've got moles of my substance B, I can now convert that to mass using the molar mass of substance B. So let's show that example here. If we start with 2.14 grams of water, that's my units, grams of water. First, I'll use something that will, a conversion factor that also involves grams of water, and that's the molar mass of water. It has 18.02 grams of water per every 1 mole of water. And so I put 18.02 grams of water on the bottom so that the grams of water cancel, and the 1 mole of water goes on top. Now I need to convert between moles of water and moles of O2 because that's what I need. It's asking me about oxygen, so I need to go to oxygen. Well, the coefficients tell me that there's 2 moles of water for 1 mole of oxygen. So that's my equality. 2 moles of water equals 1 mole of oxygen. And so I simply use that as my conversion factor. Put moles of water on the bottom, moles of oxygen on top, and now I've canceled out moles of water. And then I need to get grams of oxygen, not moles. And so I use the molar mass of oxygen because that relates grams. 16.00 grams of O2 is equal to 1 mole of O2. So I put grams on top, moles on bottom so that they cancel with the moles present. And that leaves me now with grams of O2. Now my grams of water cancel, my moles cancel, my moles of O2 cancel, and I just multiply straight through, and I'm left only with the desired unit. And I can come out and keep track of my significant figures, and I come out with 0.950 grams of O2 must have been consumed in order to generate 2.14 grams of water. Let's take this to another larger scale example. And this can be done as a group problem. If you want to pause the video, you can try to work through this on your own, but I'll walk through how we would do this. So we're given a much larger chemical equation. We have butane that is being burned in the presence of oxygen to generate carbon dioxide and water. So very similar to some of the other balanced chemical equations we were doing at the beginning of the chapter. And we're asked to find the mass of CO2 that is produced when we burn just 1 gram of butane. So what I'm asked to do is relate 2 different substances, butane to CO2. The only thing that allows me to relate 2 substances to each other is the balanced chemical equation. The balanced chemical equation does not relate masses to each other, it relates moles. So I have to follow my process. I've got compound A and I want to relate that to compound B. I first start with mass of A, convert it to moles of A, use the balanced chemical equation to convert between moles of A and moles of B, and then convert between moles of B and mass of B using the molar masses. So this is my process for finding the mass of CO2 produced from 1 gram of butane. So first off, we need to figure out the molar masses. So the molar mass of butane, again, this is just summing up the atomic masses and remembering that atomic mass units are equal to grams per mole. So it's just 4 times 12.01, that's the atomic weight of carbon, plus 10 times the atomic weight of hydrogen, and I come out with 58.14 grams per mole, and that is simply then an equality. 58.14 grams of butane is equal to 1 mole of butane, so that's my conversion factor. My molar equivalency is the relationship between the coefficients in the balanced chemical equation. There's 2 moles of butane and 8 moles of CO2. So 2 moles of butane is equal to 8 moles of CO2. That is now my molar equivalency conversion factor. And then the molar mass for CO2, we can calculate that just as above and come out with 44.01 grams is equal to 1 mole of CO2. Now that I have all of my conversion factors, I simply start with my initial given value in the top left, 1.00 grams of butane. The next conversion factor I need to use has to involve grams of butane in order to cancel grams of butane, and that would be my molar mass of butane. So 1 mole of butane is equal to 58.14 grams of butane. So grams of butane is on the bottom to cancel grams of butane on the top. Now I've got moles of butane. Then my molar equivalency conversion factor comes in to cancel moles of butane and leave me with moles of CO2. Then finally, my molar mass of CO2 comes in to cancel moles of CO2 and leave me with grams of CO2. Multiply all of this through and I come out with 3.03 grams of CO2 is produced from burning 1 gram of butane.